Okay, our next speaker for this afternoon session is Olivier Bilodeau, who works for ESET Canada, and he's going to share some interesting research on home routers and how you can build a botnet on these devices. Olivier, the stage is yours.
Thank you. Hi, everyone. All right, so Linux moves endangered or extinct, an update on this strange botnet. Today's agenda is I'll talk about the challenges of analyzing statically linked stripped ELF binaries. Thanks to the Avast presentation yesterday, some of the ELF file format will not be explained. I'll be able to go straight into the details. We'll address the moose DNA, moose herding, funny names to say description and operation, and then why in our eyes it's a strange animal, and also address the latest developments. So this presentation will have a lot of rhythm, especially since I had to reboot and lost a few minutes, and I also have a lot of ground to cover, so let's start right away. Let's just skip who am I, but I work at ESET, I guess is enough for the people here. So the static and stripped ELF binary challenge is that in ELF code, which has these properties, there are no imports, so no library calls present. All of the code is packaged together down to the kernel system call level. So there is a lot of code. The disassembler, even on the architecture that it works, for example, x86 or ARM if you have enough money, you'll get a lot of pieces of code which are all relative and all down to the syscall again. So you have to go through a lot of code in order to just get a sense of what the malware is doing. Just to give you a image of this complexity, this is Linux moves inside of Aidra. I took 3 screenshots of 3 functions, so 3 full pages of functions, and we are only at 33 lines shown in these 3 pages out of 500 lines of functions to analyze. All of this without any symbols. So let's look, for example, at a printf family of calls. So a printf in the proximity view is all linked, these functions linked together and calling internally the vprintf function, so the vfprintf internal. This, if we explode this view and get the proximity view of all of the vfprintf family, we get this. But this is all the proximity view, so we're not still at the assembly language level. So to need to get an understanding of what reverse engineering vfprintf before you realize that you are in printf code means, we have to go deeper. How bad is this? It looks like this. So this is only the vfprintf function in which there is not a single system call. So you're still not sure if you are printing anything to screen or not when you look at it. You have to figure it out. The ecosystem is also making everything worse because GCC and libc are always changing versions, updating, and when it is statically linked, all of that code is inlined into the ELF binary. So you need to, you cannot build a database of this knowledge and reuse it from time to time. Because of that problem, Aidra flirt signatures are rarely available, and for the Linux moose case, nothing was available. Additionally, you don't only have the GNU libc, which is used in embedded system malware. You have UC libc, which is the case of Linux moose. You have eglibc, glibc, and muscle. So a lot of C libraries available to look at and to try to identify before you can start looking at the malware code. The first failed attempt when trying to analyze moose was to map syscalls with an Aidra script that would document the function that was doing the syscall. But even then, as you saw in the printf case, it's still too much code to analyze with this strategy. The libc is just too big and it's too much work. So what we've been able to do is instead, and this is the advice part of the ELF challenge, we reproduce the exact environment, architecture, libc, compiler versions. Luckily, we had the exact OpenWRT revision that was used to compile Linux moves in the strings. So we were able to check out the exact version and the exact build environment. With this, we built libraries with symbol under the same conditions, and then used bindiff to map the library function. So we were able to then focus only on the malware code. As an example, this is what we were able to do with this strategy. So all of the unknown code on the left-hand side, and then all the names and the symbols loaded on the right-hand side. You select all of these lines with the confidence that you are ready to work with, and then you import all the symbols into your IDB. And so from there, you can then focus on the unknown functions, and I try to identify what they are calling, and then move on from there. In the Linux Moose case, we were able to map this way 225 functions out of the 500. So this is really helping. There's a lot of wrapper functions also, so it eliminates another bunch of functions because of the simple wrapping. Moving on to Moose DNA. Since we've given all of this information already in a report, and I guess some of you might have read it, I will go really quickly through the analysis and try to focus on the later part of the talk. But still, so that everyone understands what we're talking about, we'll still describe it. So Linux Moose was named after a string elan present in the malware executable, right here, elan2, elan3, which was the file that was the malware was downloaded as before being executed. So elan is being French-Canadian speaking. For me, was familiar with a moose, a French-Canadian moose, if you want, or not French, but anyway, Canada moose. But after the release of the white paper, thanks to internet crowdsourcing, we got other reason for the names. So maybe they were into cars after all, and they were nostalgic of the great Lotus Elan. Or maybe they're from around here, and it's based on a Slovak rock band from the 1969 that is still alive called Elan. So thanks, Robert Lipovsky, for this tip. I didn't know about that band, unfortunately. So moving on to the Moose's network capabilities, what it does that was really interesting for us was it was able to pivot through firewalls via infected routers. So, which means that it can scan internal network and is aware of its position, if it's internet reachable or not, and will adjust its behavior. It carries homemade NAT traversal code, also has a custom-made proxy service. The proxy service, interestingly, is listening on a specific port, a non-standard port, 10,073. This proxy service can only be activated by a specific whitelist of IP addresses that are sent in the CNC configuration on the initial fetch of the configuration, and then after every hour of the malware. This, the reason I insist on this mechanism is that I will get back to it because it prevented us to do some prevalence, important prevalence information. It also has a remotely configured generic network sniffer. So it sniffed a simple loop on a raw socket to get all the packets and do some pattern matching, and has DNS hijacking capabilities that are targeting specific device, TP-Link, Zytel, stuff like that. It has worm-like behavior, so it tries to replicate via aggressive scanning using up to 36 threads, some on the LAN, some on the WAN, some on close IPs, some on further IPs. It will dedicate more threads to try to find public IPs that are close by its own IP, which is an interesting behavior, knowing how firewall rules are complex and how mistakes happen in firewalls, which makes sense for them, unfortunately, not for us. It will scan on LAN, I said it. It will not reinfect an infected device. It can replicate across architectures, so a MIPS router can infect an ARM router. You'll see why later. And the CNC is made aware of new compromises. So just quickly again, this is, each line is like possible threads that are launched on all of these interfaces. The compromise protocol involves the CNC, which is active during compromise. So the advantages of this approach is that it can gather a specific binary for each architecture and will not expose the other binaries to the malware analyst. It's not all downloaded at the same time. It's fetched on purpose on infection. It can gather additional data when it's trying to infect and send to the CNC, so the CNC can be aware of maybe potentially new architectures and or environments where they could target a new binary, a new malware. The disadvantage is that if the CNC is down, no further compromises happen. It absolutely needs to be involved in the infection process. It spreads by finding routers with weak or default credentials, something that is very common in the IoT space, and only via Telnet protocol, no SSH here. It carries some anti-analysis. So the statically linked part that I mentioned earlier, while not being an active measure of anti-analysis, it's still making the reverse engineering job really tedious. So a lot more work is required than if the symbols will be there, which is something we see for most, not most, but a lot of other embedded threats. The environment is hard to reproduce because you need to be reachable from the internet in order to get interesting payloads in your honeypot. If you are natted, you will get payloads eventually, but it will take a long time before doing so. And there are misleading strings also in the binary. One of them, get cool, was actually taken down by a researcher who thought it was related to the campaign but didn't thoroughly reverse engineer the code. So he asked for the domain to be taken down, but the domain had nothing to do with the malware operation. It was just a host header put there to confuse people. So you need to be careful sometimes. So in a nutshell, this is all of the things I've just described, put in a nice diagram with a kind of a schema of when things are important. But let's move right away. So the operation now. So what we have is a malware which can have a remotely configured sniffer, so broad espionage and infiltration capability, can traverse firewall. What did they use it for? Well, unfortunately, it was stealing cookies that are already protected by HTTPS most of the time, so social network cookies. So the effectiveness is definitely debatable. When we did analyze the proxy usage in honeypot for over a month, we determined the nature of traffic, the protocol, and the targeted social networks. And here are the numbers. So in blue, you have so this is like the nature of the traffic. So in blue, you have social network traffic, which is most of what's used. And in yellow, you have the botnet meta traffic. It's using it to try to find what is its own public IP address. So most of it was for social network, not even private VPN or proxying for the malware operator. If we look down at the protocols used in that traffic, we find out that more than 75% is HTTPS, which means that for us, the PCAPs are more or less useless for at least HTTPS, where HTTPS is concerned. But HTTPS has a great property. You have a common name in the certificate, which is exchanged during the handshake, SSL handshake. So we were able to identify with high precision who was targeted. Because even if the IP was hosted on Amazon EC2, we had the certificate going through, so we knew, okay, it's hosted in EC2, but it is Instagram. So let's look at these numbers. Most of the targeting was on Twitter, Vine, a lot of Instagram traffic, and some others. In the other section, you have YouTube, Yandex, Yahoo, and Amazon Cloud, and also SoundCloud was in there. So most of these sites, if you Google, you can find that you can buy views, likes, listens, or followers on internet. So we think, because it's HTTPS, we are not 100% confident, but we think that this botnet was used to do so and was leveraging the good IP reputation of all the DSL home routers to leverage this good IP reputation to do this type of fraud. So it was more than 75% HTTPS, but in some cases, like this case here, the first connection is in HTTP and then upgraded to HTTPS. So in number one, you see the SOX proxy request and hack, which is a very simple protocol. Then the data is going through the infected machine. And in number two, you see, so the get at the top is in HTTP, but right away, the HTTP header that is sent back is a location redirect header to upgrading to HTTPS. So what we did with the HTTP is we decided to look at what was the user doing, look at their profile. So we saw some users starts with little, following little accounts close to 0. And we saw them upgrade or increase through time, mostly within a day, to, let's say, maximum 50 followers. So in this case, 36 after a few hours. Then we started looking, okay, who are they following? Most of it is internal following. So following each other to make kind of a network graph of all the fake accounts. But then in a few of them, you can spot other things. Like in this case here, signé, which is a business. So we looked at the account and if it seems legit or not. And we realized that it was following a few people and had a really few posts to be a credible account of 3,000 followers, considering that it had no Google presence at all. So it's not a web present business. So we look at that number. We were probably late already in the purchase, and we looked at it a week after, and it went up to 11K followers, so after a week. So we think that by doing this little, looking around the data, that this makes a case for the use of the botnet related to social network fraud. Then the operation also had were doing things that were preventing us to do proper tracking. The whitelist meant, the whitelist of IP address meant that we couldn't fingerprint the proxy service from any IP on the internet. Otherwise, we would have scanned the whole internet using the Rapid7 guys and their nice collaboration and service, and try to do the proper handshake for the proxy, and then list all of the public IPs which would have responded properly to the proxy handshake, which would have given us an exact prevalence number of internet reachable infected hosts. But of course, the whitelist threw that all away. We couldn't do that. So we were blind because of HTTPS enforced on social network and lack of collaboration with the major social network sites. We sent PCAPs. We asked for some tips, some help on their side, but they were not interested. And the DNS hijacking that I mentioned earlier, the rogue DNS server are never really revealed, again, because the CNC is involved in the infection. So we're not able to get the DNS IP address. If we would have been able to get them, we could have fingerprinted what phishing site or what domains were they after, what they were interested in, by comparing results on DNS query on these servers with normal DNS servers. So in a nutshell, what we have in this operation, again, the individual malware always trying to spread and do its bidding, stealing cookies, social network fraud, and then focus also on reproduction. So why do I say it's a strange animal? So it's not in the DDoS or Bitcoin mining business for an embedded threat, which is a rarity in itself. There's no x86 variant found. So we found MIPS, ARM, 2 flavors of ARM, and big Endian, little Endian of all the architectures that supports it. And it seems controlled by a single group of actors because it's all hard-coded IPs, one server. So not something that the source code was available and everyone would compile each in their own side. Some missing features that are really strange. No persistent mechanism at all. No shell access for the operator. So this is again something that we're not used to see, but since they had access to the router already through weak or default credentials, they can still anyway investigate if it's publicly accessible. So it's not a big deal, I guess. So we're thinking that this thing thought big but realized little. So the network sniffer is mostly irrelevant in the context of every site's using HTTPS right now, but it could have been used for maybe more espionage type activities. Also, the DNS hijacking is possible, but only used for very few devices, and we were never able to trigger it to see it in action. Again, it could have done with the good IP reputation of the victims. It could have done ad fraud, spam, DDoS, or just generic VPN services, but it didn't do any of that. If we look at the latest developments of the moves since the paper of the release, so after the publication, the CNC servers went dark. We were, in that time frame, actively contacting the hosts and trying to have, get hold of the IP addresses or get them to react. They were saying it was compromised server, so we wanted to help with the compromised server to have the server-side parts, server-side binaries, if any. And so all that discussion finished unanswered. After a reboot, like I said earlier, nothing would be infected anymore because of the lack of a persistent mechanism, which means that when your router starts to misbehave, you just reboot it, and oh, my internet was not working well before, I reboot, now everything's fine. You still have a binary with malware on your router's file system, but you never have a shell on your own routers, so you don't, and you can't investigate yourself most of the time. Victims were compromised via weak credentials, so they can always reinfect from another CNC server from anywhere else and then bootstrap another botnet. So we started looking at SANS internet probe data to see if we did have an impact. And this is the port 10,073 activity. And the red arrow represents when we released our paper. So again, being non-scientific, I have to admit, you know, this is just data like this. We have what we can have, and that's it. But still, there is, the things vanishes, you know. And it's around where the CNC server stopped existing, and then one reboot and no more scanning of the internet by your router. So it seems like we had an impact. So because of this, the fact that the botnet disappeared, we started being on the lookout for the next version of Moose. So I looked at during the summer, over 150 new samples targeting embedded Linux platforms. As they were, as Avas were describing yesterday, I went through a lot of Aidra, Dofloo, DNSAmp, Gafgyt, Tsunami, and whatever are naming, you know, and even in our own, it's all like source code leaked and modifications, and so it's really a mess, the nomenclature in this space right now. Still no Moose update. So we popped up the champagne and started to celebrate, but of course, anything can happen to mess with your talk. So Saturday, Moose level up. Our beloved Peter Kashina found a new Moose sample, an update. God knows where he found it. But it was Moose. And so started digging into it. New proxy service port. So this is why the data from the 10,073 port was not relevant anymore. New CNC selection algorithm, and it's tricky. We were not able to still find it, so they knew that this was a weak point in their previous malware, and they probably adapted it. And a lot of differences. So bin diffing with my previous, my best IDB, if you want, is really yielding bad results because it's compiled with a different compiler. So we'll have to go through this whole static analysis again, and we're still looking at it. And we are careful, we don't want to rely on strings with hostname and ask takedown on these domains, so we take our time on this one. So let's look at this 20 and 012 port activity. Aha, so we have something that was dead and then something taking off. Let's compare when the paper was released. Oh, so it looks like it's just to mess up with my VB talk that they released a new update or something like that. Anyway. So we think we have in our hands a new version. We can't wait to find the new CNC server and hope that the hosting providers will collaborate so we can gather more information on the server-side components and maybe kill this threat again. In conclusion, embedded malware is a different beast. In my opinion, it's not yet complex. So there's no packer or it's only UPX. It's not as advanced as the Windows counterpart. But the tools and the visibility, the telemetry, and the processes that we have will need to be improved because it's taking a while and it's still a lot of work. Especially on prevalence information, we have a lot of things to try. Right now it's a low-hanging fruit, not the malware, but the routers and the IoT industry. I'm not talking about the malware being the low-hanging fruit. So the malware operators, it's normal that they go after the least effort, the path of least resistance, and this is why they are all up on embedded devices where we don't run AV and where we have no visibility. And we don't even realize it's infected. In the case of Linux Moose, I mean the network impact is minimal, so what you can do is lose some IP reputation, but the ISPs, they don't really care. The targeted social networks don't really care. I mean, you don't even realize you're infected. And prevention is simple. So in this case, prevention is as simple as changing your default username and passwords, which is like pretty easy, just for a strong one, not for a password with a 0, of course. But this is, again, until there's a new Shellshock which goes out and targets all the routers, which would then be able to affect all of the ecosystem again, and these guys will adapt and have done, not the most specifically, but the other embedded botnet, they do adapt to vulnerabilities. And as a last piece of advice, I would say, friends, don't let friends run routers with default credentials. So before, all our antivirus product have built-in weak password detection, as we saw this morning is coming up for quite nicely for Avast. I would say, when you get to a friend's house, just hit the 192.168.1.1, try admin. If it's working, then tell them or change it for them. And if we have, all of us, if we have enough friends, then maybe we'll fix this problem a little. So I think I have some time for questions. Thank you for your attention.
And yes, we definitely can take a couple of questions. Everyone quiet. Okay, Nick.
Can you hear me?
Oh.
To get infected, the vulnerable machines have to have an administration port open on the WAN side, right? Why for this grade of machines are manufacturers still even making that a friggin' option?
I think, like, so what we saw was mostly affected were ISP provision device. And I think the ISP enables the WAN access to manage remotely. So in one case I have in mind, it was DSL, but not like a router with antennas, but just the DSL modem. So for management purposes, they were using Telnet from the WAN side to manage the routers. Of course, they changed the firewall configuration heavily to seal this from the internet, but as soon as one was infected, because of the nature of the scan, which favor local IP addresses, it was not crossing the firewall's boundary, and so reinfection would be happening all the time until we told them how it was operating, and then they understood why they had so much problem getting rid of this.
Thanks.
But yeah, of course, management, anything open from the WAN side is definitely a bad idea, and I guess most of the vendors are understanding at least that. But something easy that they could do is they already generate random passwords for the WPA key. They could just add the admin password at the same time, put it on a sticker on the box, and then you would get rid of 99% of the problem. If there is any D-Link or Linksys guy here, that's a good tip, free.
Some brands are doing that.
Yeah, some brands do now, yeah, most likely. And I know also D-Link, now they do, they intercept your browsing, HTTP browsing. They redirect you, so they force you to configure the device. But this is recent devices. And again, this stuff works, you don't touch it, you don't upgrade. Unless you're like us, who wants 802.11 AC in your network, even if though you don't need it. But that's not, we're not getting infected by this stuff.
Anyone else?
Hi. Did you report anything to the device manufacturers, and what was the response?
So in this case, no. All of the specific cases were handled through the ISP in question for the manufacturer. So they were already dealing with them. And for the others, what we found was only the DNS attack, which was using a standard channel, no exploits, no nothing. So well, I guess our approach has been more awareness and public speaking, and then vendor contacts.
Thanks.
All right, thank you very much, everyone.
So